So this is the outline of my briefing today. And first, I will briefly introduce HOSS, and then I will give you an overview on the theoretical foundation of HOSS. And after that, I will show you some selected application, and I will also cover our recent developments in HOSS. And finally, I will summarize this briefing. So HOSS stands for the Hybrid Optimization Software Suite, which is based on the combined finite discrete element method. And it is a code that we have been developing in Los Alamos for more than 12 years, and it has been widely used to simulate challenging problems and the different strain rate and space scales. And here I'm showing you 3 examples to demonstrate the applications of HOSS and the different space scales, just give you some idea about which problem that can be used to simulate using HOSS. And the first example is the simulation of micromechanics problem, which is at the millimeter scale. And the second one is the simulation of penetration in concrete, which is at the meter scale. And we also use HOSS to simulate some large scale, like kilometer scale problem, such as earthquake rupture. And recently, we incorporated different fluid solvers and fluid solid interaction solvers in HOSS to simulate a multi-physics problem. And on the right-hand side, I'm showing you a cartoon to demonstrate how we simulate hydraulic fracturing in porosity media. And in this case, we simulate both the fluid flow in the cracks as well as the fluid-driven fracture propagation and the CPG in the porous media. So, as I just mentioned, HOSS is based on the combined finite discrete element method, FDM. FDM is a hybrid continuous-discontinuous approach. It merges the advantages of both the finite element method and discrete element method. So let's use this example to demonstrate how it works. Basically, this is the simulation of split Hopkinson pressure bar test. I don't know how many of you are familiar with this experiment. But basically, in this case, we put a rock sample under some dynamic loading and generate some fracture in the rock. And this is an indirect way to measure the tensor strength. And what we are seeing in the left picture is the initial, the early stage of the simulation, and we can see that we start seeing the fracture in the rock sample, and the right picture shows the final results, and we can see that we create a bigger fracture in the middle of that rock sample. So in this case, and the early stage, we need to simulate the wave propagation and material deformation in both the rock and steel bars. And in FDM, we use the finite element method to simulate it. And once we detect a fracture or damage in the rock sample, then we dynamically insert the fracture into our system, and then some algorithms that were originally developed in the discrete element method are used to handle contact fracture and fragmentation. So from this example, we can see that in order to simulate this problem, we need to use some algorithms developed from both the finite element side and discrete element side. That's why we call this method the combined finite discrete element method. And as I just mentioned, in order to simulate this problem, we need to correctly simulate the material deformation, contact, fracture, and fragmentation. So basically, those are the key technical aspects of FDM. And in the following slides, I will briefly introduce each aspect without going through too much details. So as I just mentioned, in FDM, the material deformation is simulated using the finite element method, FEM. I guess most of the graduate students have taken some course on FEM, and I don't want to talk too much details about that method. What I want to highlight here is that, okay, the finite element portion of FDM needs to properly handle the large deformation and the large rotation of materials. And it needs to efficiently work with other portions of FDM, such as contact and fracture, and I will explain more later. And regarding the finite deformation and the finite rotation in HOSS, both the hyperelastic and the hypoelastic based formulations have been implemented. So for the hyperelastic formulation, basically we needed the information from the previous configuration and the current configuration. And in HOSS, we usually use multiplicative decomposition-based formulation to construct the constitutive law of the material. And with this multiplicative approach, we decomposed the deformation to different modes. And for the hypoelastic formulations, we need the information from the previous step and the current step. Basically, we need to calculate the rate. And in HOSS, both the strain and the stress are calculated in a material inverted coordinate system. And this local coordinate system rotates with the material. As a result, okay, we don't need to use any stress correlation in HOSS. Such as, for example, the Yarman stress rate is not needed in HOSS. So we also provided different user-defined material interfaces to simulate the material deformation. Basically, over here I'm showing you some of the interfaces that we developed in HOSS for material modeling, for contact, and for fracture. So for the material interfaces, one interface that I want to highlight here is the VUM, which is the standard WUMAT interface for APCUS. That's to say, okay, if you have any material models that were originally developed for, APCUS is a WUMAT format, you can directly use it in HOSS. And we provided those user-defined material interfaces to improve the user-friendly of HOSS. Another key aspect for material deformation is the element technology. So in theory, any type of finite element can be used in FDM. However, we prefer triangulars and tetrahedrons. That's because first, the triangular mesh can be easily generated. And most of the modern mesh generator, we can even automatically generate the mesh for complex geometries. And another reason is that, okay, the triangular mesh, the contact interaction can be relatively easy to resolve with the triangular mesh with a high computation efficiency. And moreover, more potential fracture paths are provided with the triangular mesh, especially when the mesh has the randomly orientated elements. And we have no problem with low order triangular mesh. We also call them the constant strain triangulars and constant strain tetrahedron is the volumetric locking. And we can resolve that issue with selective integration approaches. So with the finite element simulation, we can easily end up with either locking or outglassing. And sometimes we also call it zero energy modes. So it is interesting that, okay, those two mechanisms are competing with each other. So basically the reason for locking is due to the fact that the number of constraints is more than the number of degree of freedom. So to resolve that issue, okay, we need to increase the number of degrees of freedoms and reduce the constraints. And on the other hand side, the zero energy mode or outglassing is due to the fact that the number of constraints is less than the number of degree of freedoms. And in this case, okay, the solution is to introduce more constraints and reduce the number of degree of freedoms. So quite frankly, it is not that easy to find the balance point between locking and outglassing. And practically, okay, we usually use a technique which is called a selective integration approach. to avoid both locking and zero energy modes. So the basic idea of selective integration approach is very simple. So in this case, we calculate different constitutive components and different Gauss points. So as demonstrated on the left-hand side, this is a 10-noded composite element that we developed in HOSS. And in this case, the volumetric stress is calculated from a single Gauss point. Basically, this is a sort of reduced integration. And however, the diffutoric stresses are calculated from 8 Gauss points, as demonstrated in this picture. So this 10-noded composite element is decomposed into 8 sub-tetrahedrons, and each sub-tetrahedron has a single Gauss point. So this way, we can avoid both the locking and outglassing with this composite element. And another reason that we like this composite element is because first, we only need the information from the sub-tetrahedrons, and this is very convenient for fracture modeling. And another reason is that the low-order sub-elements enable robust contact interaction algorithms with relatively high computation efficiency and accuracy. So another advantage of FDM is its capability to simulate a complex contact problem, and as demonstrated in this animation, and basically here we have a group of particles with irregular shape, and each particle, all of those particles are deformable, and initially we assign some random velocity for each particle, and then those particles can freely move in the space and contact with each other. And quite frankly, this is a problem that is not easy to be simulated with that approach. And in order to simulate this problem, we usually do it in 2 steps. The first step, we need to figure out the contact relationship between particles, and we call this the contact detection. And in FDM, the contact detection algorithms should have high CPU performance and low memory usage, especially for large-scale problem. And the contact detection algorithms should also be robust to handle complex conditions, especially for dynamic problems with large displacement, like the problem that we are seeing here. Most of the contact detection algorithms can be classified into 2 bigger groups. One group is tree-based algorithms, another group is the cell-based algorithms. So as demonstrated in those 2 pictures, so for the tree-based algorithms, we construct a special tree data structure for sort and search. And for the cell-based algorithm, we first divide the computation domain into background bins, and then we conduct a sort and a search on top of that background bins. And a study has already shown that the cell-based algorithms is much faster than the tree-based algorithms. Usually, they can be more than 100 times faster than the tree-based algorithms. And HOSS features the latest generation of cell-based contact algorithms. So here I'm showing you some state-of-the-art algorithms for contact detection. And what I wanted to mention here is that the MBS algorithm, which was proposed by Professor Moniza, was the first linear contact detection algorithm, and many of the high-performance algorithms are constructed on top of MBS. And especially for students, if you are interested in contact detection algorithms, MBS is a good start point. So once we figure out the contact relationship, the next step is to calculate the contact force. And we call that process the contact interaction. And unlike the contact detection algorithms, which are mainly geometry-related algorithm, the contact interaction algorithm needs to properly handle the physics. So in that case, okay, we need to avoid the penetration, and we need to take care of the energy during the contact process, and we also need to properly handle the friction forces. So similar to the contact detection algorithm, the contact interaction algorithm needs to be robust to handle a wide range of complex problems like the dynamic particle system. And in FDM, okay, they also need to be easily implemented with finite elements and have high computational efficiency. So in computational mechanics, there are several approaches that can be used to calculate the contact force. Among them, okay, the penalty function method meets almost all the requirements that I just mentioned in the previous slide. The idea of penalty function method is very simple, as demonstrated in this picture. Okay, with this method, we allow very small penetration, and this penetration is controllable by the a penalty factor. That's to say, if we want to reduce the penetration, we can just increase the penalty factor. And the contact force is defined as a function of the penetration, and that contact force reduces the penetration and eventually separate the contact bodies. And basically, that's how it works. So in HOSS, we implemented pretension field-based penalty method. And as demonstrated in this picture, okay, with this method, we first define the pretension over contact body. And we then define the normal contact force as a function of a gradient of the pretension. And one advantage of this approach is that we can easily construct different contact law. For example, we can construct the law without energy dissipation, and we can also, if we need, okay, we can also construct the law with energy dissipation, as demonstrated here. In that case, okay, the loading and unloading need to follow different paths, and during the contact process, this model will dissipate some energy. So regarding the fracture and fragmentation in FDM, we usually use the cohesive zone model to simulate the fracture. And as demonstrated in this picture, the mechanical response of the material is decomposite into a solid matrix part and interfacial part with the cohesive zone models. And the solid part captures the deformation of the finite element, and here we can use different material models such as elastic model, plastic model, and the damage model inside each finite element. And the fracture and the fragmentation are handled by the interfacial part via the cohesive element. And the mechanical behavior of the interface is dominated by the so-called attraction and separation constitutive law, and I will show you some track curves later. And depending on when and how the interfaces are introduced into the system, or the different approaches were proposed. So one group of cohesive zone models is called the intrinsic cohesive zone models. And as demonstrated in the top left picture, in this case, the interfaces are inserted into the system at the beginning of the simulation, and those interfaces are highlighted in yellow. And to enforce the continuity of the material, strain hardening with a sufficient large slope, unit slope must be introduced. Basically, this is the first part of the traction separation curve. We call this portion the strain hardening. And this strain hardening curve, okay, basically that portion reduces the stiffness of the system artificially. And another drawback of this problem, of this approach, is that, okay, we need to introduce the interfaces everywhere from the beginning of simulation. This approach is more expensive than other approaches. So another group of cohesive zone models is called the extrinsic model. And in this case, we dynamically insert the fracture into the system based on the local stress state. And this approach avoids the artificial complaints seen in the intrinsic models. However, it may end up being time discontinuous during the transition from continue to discontinue. That's to say, at the moment that we insert the cohesive elements or interfaces into the system, okay, we may break the loading balance locally, and that okay would introduce some jumps in the system and create some fractures artificially. So in order to address those problems seen in the existing cohesive zone models, we proposed a new cohesive zone model in those animals, and we call it a unified cohesive zone model. And similar to the extrinsic cohesive zone model, our unified cohesive zone model dynamically insert the fractures into the system based on the local state variables, and those variables includes stress and strain. And to eliminate the time discontinuous issue seen in the extrinsic cohesive zone models, we developed algorithms that can smoothly transit state variables from continue to discontinue. And as demonstrated in this, the bottom left picture, the point of transition in our unified cohesive zone model is controllable through a parameter alpha. So if alpha is 0, then an intrinsic cohesive zone model is represented. If alpha is 1, then the enhanced extrinsic cohesive zone model is retrieved. So here I call our model an enhanced extrinsic cohesive zone model. And that's because our model doesn't have the time discontinuous issue. And for any other alpha between 0 and 1, a combined intrinsic and extrinsic cohesive zone model is formulated. It is a combined model because it has the features from both intrinsic and extrinsic model. And another feature that I want to mention here is that our unified cohesive zone model can simulate both the brittle and the ductile fractures. And I will show you some examples later. So in the following slides, I will show you some selected application of HOSS. So I will talk about both 2D and 3D examples. So the first example is the simulation of fracture around a 2D borehole. And as shown in the left picture, there is a 2D rock block, and in the middle there is a borehole. We apply some pressure boundary condition in the borehole to generate the fracture in the rock. And in this case, we assume that this rock block is under in-situ stress, and the horizontal stress is the minimum in-situ stress. And this problem was simulated using the unified cohesive zone model. And as shown in this animation, we can see that we dynamically inserted the fractures into the system. And in this case, okay, we plotted all of the damaged interfaces in the domain, and we can see that for this typical problem, we only got the damage around the nail fracture, and for the rest of the domain, the domain is continuous, and we can just use the finite element method to simulate the deformation of the material in most of the domain. And this is a typical problem that we used to demonstrate the capability of our unified cohesive zone model. So the second example is the simulation of triaxial core experiment of shell. And this is pieces of work that I did about 10 years ago. And back then, I used the intrinsic cohesive zone model to simulate the fracture in this case. And this work was done in collaboration with our experiment colleagues in those animals. And as shown in this animation, basically, okay, there is a rock block, and we put it between two pistons, and we then move those two pistons to break it. And in this case, because of the asymmetric of the configuration, okay, we will first generate those two bigger ones from the contact point and the corner of those two pistons. You will see it later. Yeah, you can see, okay, we have the two bigger veins. And then later, okay, we will see some horizontal fracture that's at the interface of shear layers. And we will also get some fractures in the middle of this domain. And this bottom left picture shows our final simulation results. This one shows the final fracture patterns. And the top left picture shows the experimental results. Here, I highlighted the May fracture patterns in red. And comparing our simulation results against the experimental results, we can see that our simulation results captured the May fracture patterns seen in the experimental results in this case. And okay, this is the simulation of fracture coalescence in granite. And as shown in the left picture, in this case, we put a granite sample between two pistons, and the bottom piston is fixed in space, and we just move the top one down to generate some fracture. And to study the fracture coalescence, two flaws were introduced or inverted in the rock sample, and this middle picture shows the geometry and the position of those two flaws. We have one horizontal flaw and another flaw is 45 degrees rotated. And the mid animation shows our simulation results. And in this case, we can see the stress distribution and the fracture initiation and the propagation from our simulation results. And the right picture is the highlight of the fracture patterns from the experiment. This is not the actual experiment, the picture from the experiment. We just highlighted the fracture pattern based on the experimental results. Comparing our simulation results and the experimental results, we can see that those results are very similar. Basically, in both cases, we got a V shape of fracture in the middle of those two flaws, and we also got a vertical fracture which starts at the middle of the horizontal flaw, and at the tip of those flaws we got a certain amount of fracture, and basically, okay, we can see all of those features in the experimental results as well. So we also used HOSS to study the nonlinear elasticity of rock. So this is another piece of work that integrates both the experiment and numeric simulation. Basically, this is work that was funded by our experiment team. So our experiment colleague in Los Alamos did some interesting experiment, as demonstrated in the top picture. In this case, they applied some sign pressure boundary condition to a rock bar, and then they record the velocity time history on the other end of the bar. And they did different experiments with different amplitude of the pressure. And with the FFT, they can get the resonance frequency of the bar. And what they observed from the experiment is that, okay, with the increase of the amplitude of the pressure, the resonance frequency reduces. At the beginning, our experiment colleagues didn't understand what is the mechanism that caused this nonlinear response of the rock. They asked us to do some simulations, and we built a micromechanical model for this rock. Basically, okay, we built our model using the micro CT image from part of the rock, and this middle picture shows the pore structure of our mesh, and the white space is the pore space. And we also did applied similar boundary condition as the experiment. Basically, we apply a sine wave on one end and record the velocity on the other end of that microstructure. And we did the FFT, and we observed a similar behavior as the experiment, which is shown in the bottom left picture. And here, basically, phenomenology, in our virtual or numeric simulation, we can see that, our the resonance frequency of the microstructure reduces with the increase of the amplitude of the pressure. And we did different simulations to test the sensitivity of the parameters and the results. And we figured out that the main reason caused that nonlinear response is the interaction between the grains. And by the way, in this case, for that micro structure, we have thousands of grains, and during the simulation, they are interacting with each other. And we were very happy with these results, and we published the paper a couple of years ago. This is the simulation of duct fracture in steel bar, and in this case, we used our unified cohesive zone model to simulate it. Basically, this is in this case, I just applied the velocity boundary condition to the two ends of this bar and pull it. And from the animation, we can see that before we get any fracture, the material was under large plastic deformation, and we can even see a necking in the middle of this bar. And this is a toy problem that we use to demonstrate the capability of our unified cohesive zone model in modeling duct fracture in steel. So as I mentioned earlier, HOSS has also been used to simulate the earthquake rupture. This is a piece of work done by our former PhD student from Paris. And in the earthquake rupture community, we know that in most of work assume that the rock is continuum medial. That's to say they just focus on the friction process in the bigger fault. And what we bring to the paper in this case is that, with HOSS, we can simulate not only the earthquake, the friction process in the bigger fault, but also the damage generated during the earthquake rupture process. And what we are seeing in this animation is the earthquake rupture process at different depths. And here the particle velocity is plotted in colors, and we also plotted the fracture generated during the earthquake rupture process. And from this animation results, we can see that we got more damage at a deeper depth. And we can also see that, the waveform is not as smooth as traditional simulation results. That's because the waveform interacts with the fractures. And during earthquake rupture process, both the friction in the main fault and the damage can dissipate the energy. And our student also did energy budget analysis using HOSS. And this is first of its kind of type of work, and especially in that community, in the earthquake rupture community, and we got a lot of management from this work. This is the simulation of split Hopkinson pressure bar test, and this is the one that I mentioned at the beginning of this briefing. And as shown in this animation, in this case, we put the granular sample between two steel bars, and one bar is called the instant bar, another one is the transmission bar. And in the simulation, those two bars are much longer, and here I just zoom in to focus on the fracture propagation. And in this case, we first generate some dynamic wave in the instant bar, and once the wave arrives the interface between the instant bar and the rock sample, it starts generate the fracture in the rock sample. And the right picture shows the experimental results from Sandia. And in this case, okay, we can see that this rock block is broken into two big pieces, and we also have two triangular zones close to the contact area. And basically, if we comparing our simulation results to that experimental results, we can see that okay, we also got a similar behavior. I mean, our at the end of simulation, our rock sample is broken into two big pieces with a lot of fragments, and we also have those two triangular zones. Basically, those two triangular zones was dominated by mode 2, and in the middle of the flux is dominated by mode 1. And we also compared some data between the simulation results and the experimental results. Basically, okay, we recorded the velocity time history at some point in those two bars, and then we compared our simulation results against the experimental results, and we got a very good match for the velocity time history as well. So this is the simulation of high velocity impact, and in this case, okay, we simulate a sandbox which is subject to the impact of a spheric object, and this animation shows how the ejecta was formed during the high velocity impact process, and the right picture shows the shape of the ejecta from the JPL experiment results. And we can see that, okay, our simulation, the shape of the ejecta from our simulation results is very similar to that seen in the experimental results. And this was one of the simulation that I did for the hypervelocity impact, and that was several years ago. And later on, another PhD student from Paris did extensive research on the hypervelocity impact, and she simulated some events, hypervelocity impact events in mass, and she published some papers in some top journals in that field. Okay, we also simulated the penetration in concrete, and as shown in the left animation. So basically, this is the